Welcome to the interpreter pattern. This is one of the more conceptually rich behavioral patterns in the Gang of Four catalog. By the end of this video, you will understand how to represent a small language as a tree of objects, evaluate it recursively, and just as importantly, know when this pattern is the right tool and when it is not. Imagine you are building a search filter, a rules engine, or a configuration language. Users write things like age greater than 30 and city equals London. At first you pass that string with a pile of if-else statements. But as new operators and rules are added, that code becomes a maze. Every new combination requires touching the same fragile block. The real problem is that the logic has natural grammar-like structure, but your code has none. Think of sheet music. A composer writes structured symbols, notes, rests, dynamics, each with a precise meaning. A musician does not relearn how to read music for every new piece. They apply the same rules recursively. The interpreter pattern borrows exactly this idea. Define a set of rules once as classes, then build an expression tree from those classes, and let each node evaluate itself. The interpreter pattern says, for each rule in your grammar, create a class. All classes share an abstract expression interface that declares a single interpret method. Leaf rules, things that cannot be broken down further, become terminal expressions. Rules that combine other rules become non-terminal expressions, which hold child expressions and delegate to them. A context object carries any shared state, and the client assembles the tree and calls interpret on the root. Let us walk through this step by step. The context is a simple map of variable names to boolean values. This is the shared state passed around during evaluation. The expression interface is our abstract expression, declaring one method interpret, which receives the context and returns a boolean. Variable exp is a terminal expression. It is a leaf. It looks up its name in the context and returns the stored value. And exp and or xp are non-terminal expressions. Each holds the left and right child expression. And exp calls interpret on both children and returns the logical AND of their results. Or xp does the same with or. Down in the client, we build the tree by nesting constructors, or xp at the root, with an exp on the left branch holding two variable exps, and another variable exp on the right. Calling interpret on the root recursively evaluates the whole tree, giving us true, because isAdmin and hasPlan are both true. When interpret is called on the root node, it delegates to its children, which delegate to their children all the way down to the terminal leaves. Each class is responsible for exactly one grammar rule and nothing else. This makes the grammar easy to extend. Adding an operator like not just means writing one new class. The trade-off is that for large or complex grammars, the number of classes grows rapidly, and the pattern provides no help with passing the input string into the tree in the first place. Use the interpreter pattern when you have a small stable set of grammar rules that you want to represent as composable objects. Think boolean rule engines, simple query filters, or configuration expression languages. Avoid it when your grammar is large or frequently changing. At that point, a dedicated parser generator like ANTLR will scale far better. Also note that the pattern covers evaluation only. You still need separate parsing logic to turn a raw string into the expression tree. To sum up, the interpreter pattern gives every grammar rule its own class, all sharing a single interpret method. Leaf rules are terminal expressions, compound rules are non-terminal expressions that call interpret on their children. The result is a clean, extensible design for small languages. When the grammar grows large or needs to parse raw text, reach for a dedicated parser instead. That is the honest trade-off this pattern carries.